Yeah. And let's go back to that. Good. So we are recording and everything should be all right, hopefully. Okay, so thank you very much for coming to this second workshop. Good morning. We are, please do register your attendance with the code if you are registered for this, for these 3 modules. Now, what did it say? Oh. Now, in last week's session, we did a little bit of fooling around with descriptive statistics. We looked at different data systems and things like that, data formats. Then said we describe our data. I showed you how you can use descriptive statistics to find outliers in your experimental data. And I just very briefly gave you a sort of a nudge to try out this programming software R and RStudio. Has anyone installed it in the meantime already or tried? Yeah. So you're not going to learn it overnight. You have to play around with it, but when you do that, it can be fun. Okay, so what do I want to do with you today? I don't know why it shows that. I know that my microphone is muted, so thank you. Oh, before I forget, I have decided, people have asked me how can we access the lecture recordings, because there are some people who are not on the course. And I've set up this research skills website. And on this research skills website is, you want to scan it? No, you've got it. Wait a moment, just on this research skills website, yep. There is under statistic tutorials, I think there is lecture recordings, where I will upload from YouTube the lecture recordings so that people can actually watch if they are so inclined. Okay, what do I want to do with you today? Well, I have to give you some bad news. In the last session, we said, okay, you are researchers, you collect the data, and we can summarize and describe the data. Great, fantastic. We can also check out whether there are any outliers in our data. Even better, fantastic, great. I showed you box and whisker plots, so you can see immediately what do my data look like. But at the end of the day, let's be honest, nobody cares. Nobody cares about your data. Is that a bit cynical? No, it's probably not. It's realistic. Let's say I measure the height of 10 people. 178 centimeters, 165 centimeters, and so on and so forth. Or has everybody signed in? Yeah? Good. Or For example, here I made up some data. Let's say I measure the size of a tumor in a postmortem. 8 tumors here, size in millimeter. I measure that. That's good, great, yeah. But who cares? These 8 deceased certainly don't give a damn. So why the hell do we do that? Well, we measure things, we take samples to get a wider picture. We use this to do something that is called the inductive method. So we take an inductive approach where we have some experimental data, some measurements, and from these experimental measurements, we make an educated guess about a wider population. So here we've got a sample, and here we've got a large population. I probably should draw it like that, because the sample belongs to a large population. So I can, for example, say, okay, I measure 10 people, and I use these measurements that I get from these 10 people to make an inference. If these 10 people have, let's say, the height is average of 178 centimeters, then I can say probably the average height of all the students in the room here, not just these 10, but all the students, will be also 178 centimeters. That's my best guess, right? So I can take this sample average and say probably the sample average is my best guess for the population average. And in order to sort of write this in a statistical way, what we can do is we take the average of the sample, and I showed you how we can take the average of our measurements. We said the mean equals the sum of our observations divided by n. That was the mean. We say, right, our observations, that would be the mean. That is our observations. And we say this is probably our best guess for the mean of the sample, or of the whole population. So we would say this is the estimated mean of the population, and that is usually abbreviated with the sign x bar. So an x with a line on top. X bar just simply means this is an estimate from the sample for the population. So I could, for example, here say, right, fair enough, I've got my 8 tumor patients, and if I do the calculation, I can calculate the mean for that. I think this is 58.2 millimeter in size or something like that. I've done that previously. I think that's something like that. Or we go just simply back to the height of people. That's probably more intuitive. By the way, continuous data, discrete data, continuous? Yep, you're absolutely right. When I go for the height, continuous or discrete? It's still continuous. Yeah, because it depends on, I can make it as good the measurement as I want. So there can be any number in between. Okay, so I can make an estimate from my sample. And I say, if I got a sample mean, I can use this to estimate the population mean. So far, so good. So I do my 10 measurements, or in this case, 8 measurements with the tumor. And great. I say 58.2 millimeter is on average the size of the tumor when a person dies. Great, fantastic. Amazing, I can actually do something with the data. I can make a prediction that is not just relying on these 8 or 10 specimens or observations. I can actually do something with it. But there's a problem with it. Let's go back to measuring students. I pick 10 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because you're just sitting here. And I measure you. And I get 100 and, but you don't look all really tall apart from you. So I would say average is about 175 centimeters. If I put them all together, so 175 centimeters. Good. Now I say, because today is Thursday, I want to be on the safe side. I take another group of students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I just pick them randomly, right? Will I get the same average? What do you think? Right? Will I get the same average? Not exactly the same. Let's say I get now 178 centimeters. Or with the tumor cells, I might get 62.3 millimeters. And with that, obviously, I would get another estimate for my population mean, right? Which one is correct? Which one is correct? Have I made a mistake here? No? In terms of measurements, have I made a mistake, a conceptual mistake? No. I've done everything right. Okay. So why do I get two different values? Because I take random samples. And the samples might be different. Actually, the samples are probably very much probably different from each other. Only a small bit, but they will be different from each other. How am I going to deal with that? I could do the average, and we will discuss that in a moment. It's a good idea. But I haven't done anything wrong here. So every time we take a sample, we might take another sample, and we might take another sample, we will get probably something close but still different from each other. Anyone know what this is called? This phenomenon? Huge thing in statistics. It is called the sampling error. I don't like the word error in it because it implies that we made a mistake. But we haven't made a mistake, right? It is an uncertainty. Every time we take a sample, yes, we get a value, but there is an uncertainty. How close is that to the true population mean? And there is only one population mean. If I'm, for example, interested in the average height of all students in here, I could find exactly one population mean. God knows what this is. I could measure it. Likewise, I could say I take 10 students, representative here, as a sample of all the students enrolled in the university. Huge population then. But it has one defined mean. And when I take samples, these samples will most likely be different from each other because of the sampling error. So whenever you take a sample, there will be a sampling error. I usually say to people, sampling error is like herpes. You just got it. And there's nothing you can do about it. By the way, about 80% of the UK population suffer from or are carriers of herpes virus. So it's not something that you probably will die of. So sampling error is here and it stays with us. But I still want to know what is my average population height or the average height of the or the average size of the tumor. How could we deal with that? I have my sample and let's say 178 centimeters. That's my sample. And I want to know what is the population mean. How could I deal with that? Yeah, I know. But I record on here. I hope. It always shows that now. How could I deal with that?
Assuming you can't go and just take the whole, like take more samples.
Sorry?
With the,
I could take more samples. Yeah. Now, if I take more samples, then it gets even weirder because I get more samples dotted around the sample mean. And somebody said, let's take the average. I think you said that, take the average. Yes, that is certainly a good approach. We can take several samples and then take the mean. So we take several samples. So we might have from sample 1, we have a mean. Sample 2, we have a mean. From sample 3, we have a mean, and so on and so forth. If we take n samples, we can calculate the mean, and then we can calculate the mean of this. And this actually will be a pretty good estimate. So the mean of the means will be a pretty good estimate of the population mean. Yeah, it's great. But, you know, what if I'm too lazy? Because this is time consuming. I have to measure loads of students, sometimes, you know, once or twice, some students several times. If you want to do an experiment, if you want to know how big the tumor size is, I need a lot of dead people to make sure that it's the same tumor that they died of and things like that. Not good. Yeah. We can calculate a confidence interval because that is the topic of the session today. What the hell is a confidence interval? Now, we've said it is, for example, 58.2 millimeters diameter of the cancer, or 178 centimeters height of the people. But if I was willing to accept that I probably have an uncertainty in it, I could say it's only a guess. So why don't I say it is, for example, 178.2 centimeter plus or minus a little bit. A bit, right? And this a bit might include all the different samples that the sample means that I calculated. It might include a sort of a range in which, sorry?
Between the highs and lows of deviation.
Yes, between the different measurements that I think. This is sort of estimate for the population mean. So instead of saying the population mean is 178.2 centimeters, I say it is 178.2 centimeters plus minus 10 centimeters, for example. Yeah? So plus minus, let's say 10 centimeters. So I think the population mean is between 168 centimeters, so 168.2 centimeters, and somewhere and 188.2 centimeters. This is called the lower bound. This is the upper bound. And this 10 centimeters here, this is actually called the margin of error. And I can say, right, I use just one sample maybe, or 2 or 3 or 4 samples, but not 100,000, and determine somehow what is this margin of error. And then I can say, okay, I think that the population mean is 178.2 centimeters plus minus 10 centimeters. Or I can say even, I think the population mean of all the students here is between 168.2 centimeters and 188.2 centimeters. Both expressions are equally valid. Yeah, makes sense. So I can say that I'm a little bit more sort of cautious. I don't say it is exactly bang on 178.2 centimeters, the population mean, because I don't know. Only if I measured everybody, then I could say, yes, it is exactly 170.82 0.2 centimeters. Only if I did that. But if I can't do it for one reason or another, then I have to resort to that, to the margin of error and to the upper and lower bound of this range. I'm pretty confident that the true population mean is located in there. Brilliant. How do I find these 10 centimeters? How do I find this margin of error? Yes. What you see here, in this particular case, let me highlight that. I have put in a plus and minus. Can't see that with this beautiful color. Let's do it like that. I have plus minus. This means that it is sort of symmetrical. So 168.2, 10 centimeters is the 170.8, and this then is also 10 centimeters, 188.2. So it's symmetrical, that's plus minus the margin of error. Only works from continuous data. If we don't have continuous data, as I will show you at the end of this session, you have to write it slightly different. So in this case, it is symmetrical. But how did I come up with these 10 centimeters? Actually, in my case here, this was just a sort of, I made up a number. I just as well could have said, maybe it's only 5 centimeters. Maybe it's 20 centimeters that I have as the margin of error. And of course, if it was 20 centimeters, I would have to, make this range larger. If it was smaller, if it was just 5 centimeters, I would just make this range smaller. How do I find that? How do I figure out what this margin of error could be? And with this margin of error, how could I figure out what this range, this confidence interval is? So it depends on the variance. You are absolutely right. Now let's think about for a moment what this confidence interval, let's call it for that for a moment, what this confidence interval actually depends on. Usually this confidence interval is abbreviated as CI, confidence interval, and that depends on a few factors. The first thing, and you said absolutely right, it depends on the variability. And you probably notice I've not written variance in it, I've written variability. Variability of what? Let's think about it. If, let's say, everybody in the room was 178.2 centimeters, 178.2, 178.2, 100, and so on, everybody was. There would be no variability in the population, right? Would I have to make a guess then? No, I could say, everybody is the same. There is no variability in it. I can say this time, it is definitely 178.2 centimeters because there's no variability in it. Sorry?
There is no error now.
There is no, there would not be a sampling uncertainty or sampling error when I pick sample. Everybody would be 178 centimeters. Yeah. So my confidence interval would basically be 0 if there was no variability. So what we are looking at is the variability in the population. On the other hand, if the population is incredibly diverse, so I've got, the basketball players, and then the vertically challenged, let's put it this way, right? There's a huge variability in it. So how do I find the variability of the population?
Like awesome people.
This is a little bit of a problem. Let's park that thought for a moment. Variability of the population. How we do that? You make a very good point. If we take more and more people, then it would be easier. And if at one point, if we take the entire population, then again, our confidence interval would be very small because we've measured everybody. I don't need a margin of error. So it would be sample size. So the sample size plays a role. The higher the sample size, the smaller this confidence interval. The higher the sample size, the smaller the margin of error. For the variability, the smaller the variability, the smaller the margin of error. No variability at all, I could be absolutely sure about things. Oh, sorry. I thought it's difficult to see from where I am. Okay. So how can we find the variability of the population? Right? We're looking at the variability of the population. Can we find the variability of our sample? Yes, with descriptive statistics, right? So for what we have done, observations, we said the variance sigma square equals sum of our observations minus mu squared divided by n. That was our variance for our observations, for the measurements. Yeah? You remember from last time? There was the equation for that. Now, maybe we could do something similar that we have done with the mean. We have a sample, and we can say, we take the sample mean and use that as a best guess for our population mean. We could perhaps take our observation variance and use that as a best guess for our population variance. So we use this as a guess for the population variance. Excuse me. Now that would be good if we could do that. But there is a slight hitch in it. As always, there's always another problem. We know already the lower end of our population variance. We know that this value is certainly the population variance, but probably our population variance is larger because we square everything. So this value represents the lower end of the population variance. But it won't be, close to it, or it would be close to it, but it is on the lower side. How can we make this then sort of a little bit larger? Because we know that our population variability must be equal or larger to observation variability. How can we make this observation, the sigma squared, how can we make this a little bit larger? How can I make some numbers slightly larger? Let's not play with the samples, but yes. How could I make a number a little bit larger? I could add something. Yeah. I don't know how much I would add here. The other alternative is how can I make it larger? What is the alternative? Instead of adding something, I multiply it by something, or you are absolutely right, I can multiply it by a factor, or I can do something else. Don't multiply. Divide by something a little bit smaller. Yeah. So the best estimate of the population variance would be, I take my observations, I use the estimate for the population mean, which in this case is the same as the observation mean. I square it. But instead of dividing it by n, the sample size, I divide it by n minus 1. And that actually turns out to be a pretty good estimator for the population variance. It works pretty good. This now is the estimated population variance, and it is usually abbreviated as S square. So simply here we use the sigma square for the population variance. We just use the S squared. And we can use, if we don't want this problem with the units that I mentioned the last time, we just simply can take the square root of this xi minus x bar squared divided by n minus 1 as the standard deviation, the estimated standard deviation of the population. What you see are these two equations here. One is for the observations where you divide by n, because there's sort of no uncertainty in it anyway. and 1 where you divide by n minus 1, that is where you make an estimate. And automatically, this value, or say this value, will be slightly larger than the sigma squared value. Because with the S squared, we make an estimate of the population variability. In Excel, you can use that as var.p, whereas this one here would be var.s in Excel. Have two functions in it. Both functions have totally different meaning. One is the variance of the observations. Other one is the estimated variance of the population. Make sense? Happy with that? So this is how we can estimate our variability in the population. If our sample is very varied, then the population is probably very diverse. If the sample is not very diverse, then probably the population is not very diverse. So it gives us a good estimate for the variability. Coming back to what people said about the sample size, if we have a large sample size, let's say 100 in terms of sample size, will the difference between these two things, will this difference be huge? Well, in one case, I divide by 100. In the other case, I divide by 99. You don't see a huge difference, really. Doesn't matter whether you divide by 100 or 99. So both will be very close to each other. However, if you've got a sample size of 2, n equals 2, you divide by 2. In this case, you divide by 2 minus 1, you divide by 1. The sample size, or the variance, will be different by factor 2. So the sample size plays a role. Absolutely right. Does that make sense? Yeah? So be careful, there are two equations. You need to know which one you use. You just describe your samples, you use sigma squared. If you want to do an estimate of the population variance, you use S squared, where you divide by n minus 1. So we have sample size, we have the variability. There's another factor that plays a role. That is, how certain do we want to be? How certain are we? Or do we want to be? What do I mean by that? Let's say I take a sample of 10 people and I've got 168.2 centimeter to 188.2 centimeter. Very often confidence intervals are written like that. That is where I think my average population mean is located, in between. Now, let's say somebody does similar measurements and says, well, the population mean that I found is 109 90 centimeters. That's my population average. So we measure 168 to 188, and another person says, oh, it's 190 centimeters. Would we say that this sample that this other person has measured with the 190 centimeters comes from our population? No, because we think our population is between this one and this one here. We say it's 100, they say 190 centimeters. So we would basically reject the claim that it comes from the same population, right? So we make a sort of a rejection. Now, what we can do is, and let me just quickly change the way we see that. We could set up a sort of a table. Something like that. And for this example, or to illustrate what we're doing here, is I want you to imagine you are at an airport. Everybody ever been at an airport? Probably don't have to tell you what it's like. And what do you do at an airport when you've got, say, 3 hours stay over? What do you do? Duty free. Nah, you do something much better. Have a drink. Yeah, have a free drink, right? Oh, there is. There is. Have you ever been to these airline lounges? Yeah? Cool stuff, isn't it? You get in, you get your canapes, you get your champagne, you get the waitress or the waiter, and you know, all these things.
Not for economy people.
Yeah, but you see, that is where you are wrong. That is where you are wrong. Because what you need to do is you go up to this entrance to the air lounge, gold lounge, premium lounge, whatever. There's usually a gorilla, a bouncer. Bouncer looks at you. What the hell do you want here? And what do you say? I want to go in. Yeah? The bouncer will say, are you a member? What do you say? Yeah, of course I'm a member. I just don't have my card on me because I just registered and I don't think the system has updated yet, but I'm a member, I'm paying for it, and I want to go in. Which causes the gorilla a bit of a headache, right? What should the gorilla do? Reject? Yes or no? The system hasn't updated yet. Here is should reject. Yes or no. Now the gorilla has basically 4 options. Yeah. If they look at you, right, in your dreams, baby, right? You are not coming in here. And I was just blatantly lying. Reject. And the bouncer should have rejected me. So they were absolutely right. If, however, I said the truth, I did pay, and the bouncer is not sure, would be right here as well. Don't reject me and say, hop in, help yourself. That would be ideal scenario, right? We have got 2 more cases where the bouncer makes an error. If they reject me, but they should not reject me because actually I told the truth. Yeah, this is one error. And the other one is if they said, yeah, come in, and I lied. And I go like, yes, right? Another win for Team Clapper, right? These are 2 errors that the bouncer could make. Which error could cost the airline dearly, could cost the bouncer their job? In this case, they reject me, although I am true. Why is that costly? Exactly, I will never fly with this airliner again. So this one here, because it's costly, it's called a type 1 error. It's usually abbreviated with alpha. The other one here, where the bouncer doesn't reject me and said, come in, what's the worst case that I can do? I mean, I can eat all the caviar, don't like caviar. Tastes like blackberry jam mixed with fish. I can drink the champagne, and I can have my wicked way with the waitress. But, you know, wow, maybe not. Yeah, but that's the worst case that could happen. So it's not really a big deal. And as you say, maybe nobody will ever find out. Yeah, because the bouncer says, if anyone finds out, then, you know, I get it in the neck. But at least the customer is happy. So this is a type 2 error. That's usually abbreviated with beta. But this one here, that is the costly one. And we want to keep that sort of fairly small. If we keep it too small, then we would increase this one here. Because if the bouncer is too shy and says, I want this to be almost 0, it means they won't reject anyone. So we need to find a sort of the Goldilocks, the right zone between for this alpha. We want it a little bit, but not too much. And actually, we can set it to whatever we want. It is at the discretion of the bouncer. If the bouncer is risk averse, they will keep that alpha very low, close to 0. If the bouncer says, I have a very strong view about, middle-aged white men. The middle-aged, I'm flattering myself. I consider myself as old, but middle-aged white men are not coming into the air lounge. I will set that quite high. So I will reject even if they shouldn't be rejected. I don't give a flying flamingo if they complain or not. Right? So we can set alpha, and it also has another name. Alpha is usually referred to as the significance level. We can set this to whatever we want. We can, very often, it will be set to 5% or 0.05. But there is no, how shall I say, law in the universe that we have to set it to 5%. We could set it to 1%. We could set it to 0.1%. It is at our discretion. So, coming back to our example here, the confidence interval depends on alpha. The smaller alpha, the more tolerant I need to be. The smaller this type 1 error. The larger alpha means a narrower confidence interval. Okay? Shall we do a 5-minute break? Yeah, because we have one more thing that we need to look at. Back in, yeah? Yeah.
Earlier when we were doing the S, what does S stand for?
S stands for, it's the same as the sigma, the standard deviation. Yeah. Only it's not the Greek letter, it is just simply normal S to indicate that this is an estimate.
Okay.
Yeah?
Okay.
Make sense?
Yeah.
Good. 5 minutes? Make sense? I'll leave it to you in a second. I don't know if it is still active.
I would have to basically like in the train station and the train station in London. Yeah. Yeah.
Okay, good. It's, But it's not your Okay, shall we? We are probably pretty close to forward again. Most people back. So, bless you. We said the confidence interval, or if we like, the margin of error, MOE, depends on the variability, variance, or let's do it standard deviation. Standard deviation of the population. And we said we have to estimate that because we don't know it. Depends on the sample size. The larger the sample size, the more information I have, and the narrower I can make this confidence interval. And we said it depends also on the significance level alpha, how sure we want to be when we reject things. Yeah, I don't know where you find alpha on a Windows and what the key combination is if you type that on a computer. Not entirely sure how you do that. So these are the criteria, and maybe we can come up with an equation for that. And in fact, we can, because the margin of error equals S. That is our standard deviation that we estimate. Divided by the square root of n by the square root of the sample size multiplied by a factor, let's call it T crit. What is this T crit? This T crit is referred to as the critical T value. And this critical T value is sort of a factor that makes this sort of a proper equation. This critical T value contains the value for alpha, depends on the value for alpha. It also depends on the sample size on n, although not entirely true. Does not depend on n, it depends actually on what is known as the degrees of freedom. This is basically when I have the sum of, let's say, 3 numbers. So let's say I've got 1 plus 2 plus 3. That is, what is that, 6. How many of these numbers do I actually know? I have 3 places here. How many of these numbers do I need to know in order to get 6? The answer is I need to know at least 2 numbers. Then I can figure out the third one myself, right? If I have 1 plus 2 and it should be 6, I know that the third one must be 3. So I need to know at least 2 numbers. If I have 1 plus 2.5, again, I need to know at least 2 numbers to figure out this one. So the degrees of freedom are given by n minus 1. That is what I need here. And that is what this t value actually says. The t value also has another importance because the t stands for a sort of a population distribution. What the hell is a population distribution? If I look at the height of people, I will probably find, so here's the height. I will probably find that the height has a particular distribution in the population, whatever population I will look at. There are few people who are vertically challenged. And there are a few people who are extremely tall. But the majority of these people is probably somewhere in between here. Does anyone know what this distribution is called? It's the normal distribution. Other word for normal in this case? Right? It's a bell curve, absolutely right. Who discovered it? It's a Gaussian distribution. Very common Gaussian distribution or normal distribution when we are talking about observations for continuous data. Continuous data. We can't use it for discrete data. Right? Typical feature is that the mode of this normal distribution is also the population mean. And the spread of this population represents usually the standard deviation in the population. Okay, so that is the normal distribution. The t distribution looks very similar, but has just a little bit fatter tails. Looks a little bit like that. And this t distribution, there is not just one t distribution, there are several t distributions depending on the degrees of freedom. But we don't need to worry about that for the time being. So that is what this t value indicates. So where do we find this t value? We can calculate S, we can calculate square root n. So we can calculate this term here. This term actually also has a name. It's called the standard error of the mean. Because that's what we are looking at the mean, or abbreviated SEM. Or sometimes it is just simply abbreviated as SE, as standard error. Here in this case, because it's the mean. Where do we find this t value? Now, you would usually have to use tables, statistical tables, where you find this t value, or you can use Excel or Google Sheets, because there is a very handy function in it, equals t dot inv dot 2t, and it will ask you for alpha and for the number, for the degrees of freedom. So t-inv 2t, alpha, and degrees of freedom. So in our case here, let's say we want to have an alpha significance level standard of 5%, 0.05. And we might go for the tumor things where we had 8 measurements. So we would have 8 minus 1. These are the degrees of freedom, right? If I can find that. Okay, so here is the function that you see, t-inf.2t, 0.05 and 7, and we get a t-value of 2.36 or something like that. That is sort of a factor that we use to make this margin of error a valid equation. Yeah. And now, in theory, we could calculate that. We could put that in and calculate 2.36 times S over square root. We had 8 observations. That would be square root 8. And the S we could calculate. That would be our margin of error. And you could easily do that in Excel. But I am of a very lazy persuasion, and so should you be, because there is a fantastic online calculator. And I show you the QR code for that. May I suggest that you scan this and bookmark the site for it? Sorry?
Is this in Moodle also?
I will send out the link. I think it is in Moodle as well. Yeah. Because you will find this extremely useful for the rest of your statistics life. You just need to know what you're doing with that. But I'll send out the link. If you scan that and go on the tab up there to what is called a 2-sample t-test, don't worry about the name, on this tab, you find the option where you can actually put in numbers Here are our tumor size numbers. And it will, very conveniently, the moment. And I edit this. Okay, I need to get up then. You can immediately see the margin of error 23.42. It calculates the margin of error for you. And it even calculates the lower and upper bound for the confidence interval. Ignore this part here, ignore this one, we'll use that next time. So this calculator will, as soon as you provide it with the numbers that you measure for your observations, it will do everything for you. That makes sense. Use this calculator. It is really good. Now, what does the confidence interval actually tell us? We were talking about it, and we have seen how we can calculate it. But what does it mean? And what you will find is a lot of people have a lot of ideas about what a confidence interval actually means. And you will also find that lots of these ideas are totally wrong, or at least not correct. People say, okay, a 95% confidence interval gives us the range where I am 95% sure. I'm not 95% sure about something. I mean, I am always sure about things. My wife will tell you that I'm always wrong. Married life. So in a way, the calculation for a confidence interval is pretty straightforward, simple. T times S over square root n, and you get your margin of error. Job done. But actually, the physical interpretation is very challenging. It is almost like a sort of a convention. Everybody uses it, but nobody really understands what it means. The true meaning of a confidence interval is actually quite convoluted, because how many samples have we used to calculate this confidence interval that we just did? How many samples did we have? Well, we had 8 observations, but we had only 1 sample, right? So we can calculate a confidence interval based on just 1 sample that we take. Or in other words, every time we take a sample, we can calculate a confidence interval. And the true meaning of confidence interval is we don't take just 1 sample. We take 100 samples. We are not physically doing it, but that is what the meaning of confidence interval is. We take 100 samples and 100 confidence intervals, because for each sample, we can calculate a confidence interval. So that is what it might look like. And this calculation that gives us the confidence interval is designed so that 95%, that's the 100 minus alpha, that the 95% of all these samples, all these confidence intervals contain the true population mean. As I indicated here. 95 of them contain it. You see this one here? This is a confidence interval that we got from another sample. But it doesn't contain the true population mean. That's one of these 5 that won't. Again, it is on average, it will contain 95% of the sample, of the confidence intervals contain the true population. That is the true meaning of a confidence interval, but nobody gives a damn because everybody says, oh yeah, it's a confidence interval. But that is the true meaning. It's a sort of a convention. Everybody turns the light on, but nobody thinks about how does it work, right? But that's the true meaning of a confidence interval. So you have seen how you can calculate a confidence interval. Actually, usually you won't calculate a confidence interval because you would use a calculator. Here is also an R script that I've written, which basically shows you how you would do that in R. So you've got your sample data here. You would calculate the length of the data. So it's basically, in this case, we've got, was it? Yeah, microphone, go away. We've got 1, 2, 3, 4, 5, 6 data points. So that would give you the length of the data. That would give you 6. It calculates the sample mean. It calculates the sample standard deviation. Well, the estimated standard deviation, I should say. And you go for a confidence level that is 1 minus alpha. That would be 0.95, but that's entirely up to you how you set that. And you calculate the error of margin here and the confidence interval with this one here. Brilliant. Happy with that confidence interval? But the big but is you can only use this calculation if indeed your population shows something like a normal distribution. If your population does not show a normal distribution, hands off. You can't calculate the confidence interval for a population that is not normal distributed, at least not with this calculation. You would have to use some other tricks, and we can discuss that. That's a bit of a bummer because sometimes we have data that are not normal distributed. We have data, and the normal distribution is only valid if the data are continuous. If your data are not continuous, if you have discrete data, then you can't do it anyway, full stop, because it will never be normal distributed. Might look like normal distributed, but it is not the definition, not normal, and therefore you can't use this calculation. Can look at other distributions. Here is a typical distribution. Well, actually, it's not a distribution. It is my favorite breakfast. It is cinnamon and raisin bagels. Who likes cinnamon and raisin bagels? Hands up. Who hates them? Hands up. Okay, good, fair enough. I don't judge you. Yeah, I don't think per se you are bad people. You should reevaluate your choices in life, right? With lots of butter on it. I mean, your arteries go probably, oh, no. Your taste buds go, yes. So what we could do, for example, we could measure what is, on average, the number of raisins in one of these cinnamon raisin bagels. And what we will find is that this usually, or very often, will follow what is called a Poisson distribution. A Poisson distribution is for discrete data, and it measures the rate, which is events per time or events in a given space. These are known as rates. So we might have 5 raisins in a bagel. That would be a rate. We might have 20 raisins in a bagel, in 5 bagels. That would be also a rate. And we could, in a way, we could extrapolate and say, how many raisins on average will we expect in a bagel? So we can calculate it. It is discrete. You can only have whole numbers of raisins unless you chop them, but that's illegal. Okay, so Poisson distribution, very typical for discrete data, for count data. When does a Poisson distribution apply? There are a few rules. The rates must be constant. Events must be, we must be able to separate events. It means 2 raisins can't be in the same spot. And events are independent of each other. Independent of each other. Let me give you an example. I want to check what is, on average, the use of a toilet in a pub per hour. Right? So per hour, that is a time frame. And I count how many people go to the toilet in a given hour. That would be a typical Poisson distribution because it's discrete data. The rate must be constant. That means I can only measure a time span where actually people go at a fairly constant rate. So if I say I look at Friday night at 11 o'clock when everybody needs the toilet, and I then compare that to Saturday morning at 6 o'clock in the morning when the pub is closed, that would not That would not make sense. The rates would be different. I need to be able to count people individually. So actually, it would not be right if all of a sudden 5 people at the same time went through. I can't separate the events from that. So therefore, that would be a violation of point 2. And the independent thing, that is sometimes a bit of a problem, because when we come to this pub example, it is gender specific. That's at least my observation. I'm not a sexist in any way, but I discovered that with ladies, you can't apply a Poisson distribution, because I found that they usually turn up in sort of packs. It's a little bit like, they're having their drink and things like that, and then one says to the other, "Shall we go to the toilet?" That usually is, as far as I understand, I'm a guy, right? I have absolutely no insight into the female psyche. This usually means, they are not going for when nature calls. It is more, I need to tell you about what my boyfriend did the other night, and that was absolutely terrible. So they usually turn up in packs. Male usually is more leaning towards a Poisson distribution, because if there's a rugby team and you say to the person sitting next to the guy sitting next to you, "Shall we quickly go to the toilet?" It is like, maybe not, right? But what do I know? I don't play rugby anyway. So these are sort of the restrictions for Poisson distribution. How do we find the confidence interval for Poisson distribution, for this rate? Guess what? The fantastic thing is that this online calculator will also do a confidence interval for Poisson distribution. Yeah, I know that the microphone is turned off. All you need to do is you need to go to count data. And let's say, just remove this one here, don't need that. Let's say we have 20 raisins in 4 bagels. So 20 events. Here it is days, but you can imagine that this is bagels. Yeah. It will calculate the confidence interval. Of course, we can calculate the estimate population. 20 divided by 4, we would expect 5 raisins. The confidence interval for that is 3.1 to 7.7. That is the 95% confidence interval for the number of raisins on average for our confidence interval for count data. Does that make sense? The calculation, not for the faint-hearted. Again, it would be a standard error, but this time it is discrete data, and they do not follow this normal distribution. They actually follow a slightly different, they follow a Poisson distribution, which you need to take into account. But if you've got this calculator, job done. Happy with that? Any questions? I killed you. On Tuesday, we've got the next session, I think, in Kane Seminar Room 6. It gets a little bit wilder even, because you can do fantastic things with confidence intervals. Are you ready for it? Not today. Thank you very much. And if you've got any questions, email me. I'm very happy to respond. Thank you. I hope it will be available. I have no idea what happens to the recording because they nicked my Teams. So I hope there will be a recording.